So hi everyone, good afternoon. Thanks for coming to the talk, although it's almost the end of the conference. So this is Tackle work, joint work with Marcello Federico from FBK, Italy, and I'm from the University of Amsterdam. So today we are going to talk about how we can dynamically refine or reshape the search space of phrase-based SMT with particular respect to word reordering. So first, a bit of motivation. So why phrase-based SMT? So as we all know, phrase-based SMT does not assume a structural representation of the sentence, and because of that, it can only model local dependencies between words. However, there are important advantages compared to tree-based models. Namely, we have typically smaller translation models, faster decoding, and this kind of system of approach is also remains very competitive for translating between similar language pairs. So for all these reasons, phrase-based SMT appears as the most popular framework, at least in SMT production scenarios today. However, one of the major shortcomings of this approach is that it does not handle well reordering. In particular, it does not capture well long-range reordering. So the goal of this work is to dynamically shape the space of reorderings that are explored during search. And by doing this, we aim at achieving better translation and faster decoding with loose reordering constraints. So this is just a slide to give a quick overview of the decoding process of phrase-based SMT. We are already familiar with that, so just to remind ourselves that in phrase-based SMT, the target output is produced from left to right. At the same time, we are exploring different segmentation of the input, and we are trying potentially all the possible permutations of the phrases, of the source phrases. So then we have different models that give scores to different aspects of our translation hypothesis. So typically we have the translation model scores, language model scores, and reordering or distortion scores. And these are all combined log linearly, as you can see in this picture. And the weight of these models are tuned to optimize translation quality on a depth set. So what's important to retain from here is that we are trying to explore a very large number of permutations during translation. And that's what I mean by the reordering search space. So let's see a bit more in detail how this works. So because searching over all permutations is known to be NP hard, this huge space is actually it's never explored during decoding, but we apply hard reordering constraints on the distances between the words, and this is going to define the maximum jump that we can perform during decoding. So we can see this visually in two different ways. So you can So you can think that you have translated this word, and now you have to decide where you are going to jump next. Or you can represent it as a matrix where the cost of each jump simply corresponds to the distortion, which is the distance between the input words. So how the reordering constraint works, it works by simply limiting the maximum length of the jump that we can perform. So these jumps here are never going to be performed if we set the distortion limit to 3. Or if you look in the matrix representation, these jumps are never going to be explored during search. So does this work? So the intuition of the distortion limit is that languages tend to arrange their words in similar orders, but we know that this is not always the case. So if we look at these word alignment matrices between Arabic English, we can see that these are very prototypical example of sentence pair. So we can see from the first example that indeed the distortion limit is a good fit. Why? Because most of the points lie on the diagonal, and only the points that you can see here stand for local reorderings or swap of adjacent words. So we can hope that this type of reordering is going to be well captured by phrases. However, if you look at the second example, you can see that some points lie quite far from the diagonal, and these points are not alignment errors, but most of the times they are very crucial verbs, crucial words, like verbs that are very important to translate in the correct place to preserve the meaning of the input sentence. A few more examples in German English, and this is also due to the different position of the verb in German with respect to English. Okay, here is an example. So you can see we have an Arabic sentence, and we have the reference translation and the baseline translation. This is quite known to everybody who has worked with Arabic English. The target verb should be placed much far from his original position to have a correct translation. And what happens most of the time is that it will be simply output at the beginning of the sentence, so we basically lose the whole meaning of the sentence. But if you look at the rest of the sentence, you can see that we have almost a perfect match with the reference translation. Okay, so how can we cope with these cases? Currently, what people do is simply increasing the distortion limit, but this has a very bad impact on the reordering search space. You can think that for this simple example, so a sentence of 10 words, by increasing the distortion limit from 3 to 7, we are moving from a number of permutations around 3,000 to more than 1 million. So this very coarse definition of the reordering search space, it has some negative effects, not only slower decoding, but also worse translation, because the models that we have today, they're not able to guide search through this very large space. So that's why we see in evaluation campaigns and so on, the best performing system typically have a distortion limit of around 6 or 7 words, which is clearly not enough to capture all the reordering that is happening in for instance, Arabic English. So the model that we propose to address this problem is called the word after word reordering model, or WOW model. And this doesn't work. So the way it works is by formulating the reordering problem as a binary decision task. So basically we want to predict whether any input word J should be translated right after an input word I. And we solve this by training a maximum entropy classifier using binary features encoding properties of the word I and J, the respective context, and also the words between I and J. So you can see that the correct reordering can be inferred from the reference translation, and that's how we generate positive and negative examples for our training. And these are some feature examples. So we can have the words at position I and J, we can have part of speech at the position I and J, and we can have also features of the words comprised between I and J. Okay, now the interesting part comes is, so how are we going to use this model in search once we have trained it? The usual approach is to add it as an additional feature function, and that we can do, and that we actually experiment with that. But we also introduce a novel way to integrate this model into search, and that's what we call early reordering pruning. And the effect of early reordering pruning is precisely to dynamically prune the space of reorderings that we explore during search. So how does this work more in practice? So remember that in standard search, what we do is exploring all the jumps that lie within a fixed distortion limit, and then we let them be scored by all the models. Instead, what we do now, we are going to only explore the long reorderings that are most likely according to this novel reordering model. So we can, before hypothesis expansion, we can query the new reordering model and get scores for each of the possible jumps, which are represented by these numbers. And then we can apply histogram and threshold pruning only based on this particular score to all the jumps that are available at this point. And for instance, in this case, we might want to prune all these possible jumps. So now we are going to explore to proceed only in this, following the jumps that are most likely according to the model, to the reordering model. But then we also note that this might be risky because we may want to make sure that at least window of local reordering around the current position is always explored. So we do this by introducing another parameter which defines a kind of safe zone where we always proceed with reordering. So we can decide that everything that lies within a distortion limit of 2 is always explored, and only the longer reorderings that are most likely according to the reordering model will be explored. So going back to the matrix visualization, we can represent this with these zones. So before we only had a allowed zone, the white one, and then one that is disallowed by the distortion limit. Now we have actually 3 areas. The white areas is not prunable, so we are always going to explore it. Then we have a prunable zone where we will go only if the model tells us it is a good idea to do so. And then we still have a space of very long-range reordering that we do not want to explore. Okay, so now let's look at the experiments. So we have tested our approach on the NIST-MT09 Eval 09 Newswire benchmark for Arabic English. All our systems include the state-of-the-art hierarchical lexicalized reordering models, and we also include in the baseline the so-called early distortion cause, which was proposed by Moore and Quirk 2007, because this turns out to be important to maintain good performance with high distortion limit. And then we evaluate our output by blue for lexical match and local order, but we also employ a reordering specific metric that does not look at the lexical match, but only at the way words are reordered during translation. And we also consider 2 testing conditions, one with the medium scale language model and a regular stack size of 200, and then a larger scale condition with a larger language model and a larger stack size. So here are the results. You can see here the early reordering pruning parameters that we are using. So we have a non-prunable zone of width 5, so everything that's within 5 is always explored, and we prune the reordering based on the word after word reordering score with histogram pruning of 3 and threshold pruning of 0.1. And in this plot, we can see blue on the x-axis and the reordering scored on the y-axis. So what you can see here is that we start from this is our baseline actually, the distortion limit of 8, and increasing the distortion limit, as I anticipated earlier, has a bad impact both on blue score and on reordering score. However, when we integrate the approach that I just presented, we have an improvement according to both metrics. And what's important to see is also the difference with respect to the baseline with the large distortion limit, because this baseline was capable of capturing this long reordering, and this baseline was not at all. And we can also look at decoding times. So this is also a nice result, because as you can imagine, increasing the distortion limit has a very bad impact on efficiency. But when we apply our approach, we have a reduction in time also compared to the original baseline with distortion limit of 8. In the large scale, we have a similar result, actually even a bit better. So introducing the new approach results in better blue score and slightly better reordering score compared to the baseline. and a very large gap is observed with respect to the distortion limit 18 baseline. And again, similar trends in decoding time. So we are doing better than the large distortion baseline, of course, but we are also doing slightly better than the distortion limit 8 baseline. At the same time, we have better translation quality. Okay, and you can find more metrics and language pairs, namely German, English, and also a comparison with the hierarchical SMT in my thesis. Yeah. So just to give you an example, this is the sentence that we have seen before with this very difficult reordering, and now this is captured by the new model, but at the same time we didn't observe any increase in the translation time. Okay, so in conclusion, phrase base remains a strong baseline in many language pairs, but this is typically at the expense of long-range reordering phenomena. And in this work, we have presented a method to capture these long-range reordering phenomena in phrase-based SMT without sacrificing efficiency. Our results show better reordering accuracy and translation quality in a large-scale Arabic-English translation system. And what you can think of about this method is that it could be seen as a mix of pre-ordering approach and decoding time reordering approaches, because during search, we are alternating the phase of regular hypothesis expansion, where we use all the translation and language models and so on. And we alternate this with phases where we only trust the monolingual reordering model to take some decision during search. And the last thing that I want to say is that a similar idea may be applied to other reordering models, probably not to the phrase orientation models, because they don't discriminate enough between different jumps, and that's precisely the reason that I came up with my own model. But recently, new models have been proposed that could be applied with this technique. For instance, we can think about the operation sequence model by Durrani, and also there was another work by Isao Gotto last year, who could really fit well to this idea. So that's it, and I'm ready to take your questions.
Very nice talk, thanks. I wonder whether you also compared to a distance-based distortion some systems implement that grows linearly until a specific jump limit and then quadratic?
So it's an alternative to the distortion limit?
No,
understand.
So usually we have the distance-based jump cost.
Yes, okay.
And some systems implement this in a way that you apply linear jump cost up to a certain limit, like 5 or 7, and after that it grows quadratically.
Okay, no, I haven't compared to that, but my feeling is that that will not help you very much to reshape the reordering search space, because it's not aware at all of the words that you are translating at this point.
Well,
because it's still based on the distance, right? It's just a different function, but of the distance.
It's not very informed about reordering, good or bad reordering, but it allows you to prune away long jumps in cases where other models, the language model, for instance, don't tell you it's good. So you would be able to prune long reorderings early.
Yeah, actually, this early distortion cost that I mentioned, it goes in that direction. So it's still the regular distortion cost in the base, but it includes an estimate of the reordering cost that you will incur if you just complete your hypothesis monotonically. So this kind of address that problem that usually we have with long reordering, that they are penalized too late. This really addressed that problem, and we have seen important improvements with this function, and that's why we integrate it in all our systems. Yeah.
Yeah, so in phrase-based reordering, you have, when the part that you have already translated is also available in principle for example, learning the classifier. So I didn't understand if you also have considered using the translation generated so far as context for the classifier.
Okay. No, that's a good question. So all our features are based on the source side, and they're based on the original order of the input sentence. They do not condition on the decoding history so far. And the reason is that you can pre-compute all the word-to-word costs before starting the search. So you can create a matrix of this kind before doing actual search. These numbers are not going to change during decoding.
Okay, thanks.
And that allows for an efficient integration.
Hi, thanks. But you could have conditioned on the, well, maybe it would just make it sparser, but you could have conditioned on the word, the previous word, having been translated out of order, right? Say the gray word right now, it already incurs a distortion cost, suppose. You could have conditioned on that, right? Yeah,
on this one?
The one yes, so you're trying to decide if you're going to skip. You can at least
we definitely condition on that. So these are the features.
All right, sorry, I missed that, sorry.
No, that's fine. So everything that is observed in the input sentence can be used. So there is no limit to the context that you can use, and in fact, we can use, even if it's a very long jump, we can use potentially all the words that are comprised between I, J. We can use the word before I, the word after J, for instance, and we use it in our classifier.
So I have a question as well. So, so you limit the space of, say, permutations, right? I mean, by predicting as you go. Mm-hmm. Do you know what is the space that is remaining? Do you have any kind of either empirical or intuitive hunch on whether it could be in any way, for example, similar to the ITG hypothesis, where, you know, which we've heard very often?
You mean the size of the
space?
Yeah,
I mean the kind of jumps that you're allowing. You have a distribution over the possible jumps that can happen. Yeah. I saw that the alignment matrix where you show the shades, basically, right? So is that, I mean, can you say something about whether, you know, obviously, and you know, naturally, it's like you know, closer to the diagonal, but did you look at across a corpus of, did you decode what's going on in terms of reorderings that are happening?
So I counted the number of long reorderings. Actually, I counted the number of jumps, mm-hmm. And then I break it down by the length of the jump. And I don't have this in the slides, I think. No, I don't have it here. But it's quite interesting to see, because you see that the long reorderings actually do happen. And they happen a bit less frequently than in the baseline with the high distortion limit. But that's also what we want, because we know that that baseline may tend to over-reorder. Mm-hmm. So, but at least, I verified that these reorderings still happen with this model, yeah. Okay. But many less hypotheses are considered, of course.
Okay, thanks, yeah. Okay, we're finished. I think some people might want to go to the next talk somewhere else. Let's thank Arianna. Okay, thank you all. We're finished.